The future is watching. Welcome to Opcode Virtual Summit.
So yeah, we're back. So I was saying, so we're gonna be talking about Windows ARM64 exploitation. So basically, I've had an ARM64 Windows laptop for around a year now, I guess. And was it 1 year? Something like that. Yeah, let's say a year. And initially, I just like used it for like one afternoon to dump it to work on ARM64. And that's it, I never really touched it anymore. Although it's quite a nice machine, like it's very light, like the battery lasts like for a very long time, like more than 10 hours. So overall, it's quite a good laptop, but I didn't really use it to do like more security research. Also, like if you try to use Visual Studio on it, like it's like pretty slow. But yeah, other than that, it works quite well. There's some applications, like WireGuard, that were not ported to ARM64 yet. But otherwise, most of the stuff work fine. There's 32-bit emulation, all those things. So yeah, I didn't really do more research on it until I saw the exploit that Chumpy released for SMBGhost. I was like, oh, that's quite cool, actually, like a good opportunity to look more into details of or like remote exploitation works now on Windows 10, especially like with all those like security mitigations happening. I didn't write any exploit in a long time, and I was aware that could be a good opportunity to also learn ARM. So I worked on that over the past 2 weeks, I guess. Even like in the last opcode, I mentioned it. I was like, oh, like I got stuck on something, so which was like ARM64 related for a project. So that was for that one. And one of the thing, start zoom here. Yeah, one of the thing which is quite interesting with this is like a lot of things are like very similar and a lot of things are like completely different. So that's pretty cool. So as you can see, I'm doing all the checkbox of having an exploit. So I found the name, which is like the name of my dog, and I called it SMBaloo. So it's nice. And instead of having like a scary name and scary thing, I was like, well, what about just making it like something like more calm and more peaceful and something nice and friendly to look at, instead of like finding those names like Corona Blue or like those like scary names that no one really care about, and then people keep reusing everywhere. So for this, so unlike Grok, I didn't prepare any slides, but that blog post is just available now. There is the exploit on GitHub, which is available. So I'm just gonna like try just gonna do it in a Twitch format where I'm just gonna like take my blog post and break it down and use it as a support for my presentation today. So first of all, because and also that's something I've been complaining a lot every time when I like when I get people like speak, or when we are in the review board of I'm on the review board of a few conferences, is people not giving acknowledgement of references to like people who have been doing like research on a past subject, because usually it's always built on top of a lot of like other people research, and I think it's normal that we can acknowledge and credit them, especially if you're like new and you want to learn. It's always good to have like reference link that you can go to read, so it completes like whatever you want to learn about. So regarding SMBGhost, like hats off to Huge Org for his great blog post about the vulnerability, and as far as I know, is like the first blog post I've seen on it. It was explaining how to do physical memory read from the vulnerability, but also the vulnerability itself, which was quite nice. and Chompy for POC exploit, which is pretty good. My ARM64 exploit is like heavily based on it, so all the SMB features are just like based on the exploit, and whatever is different is just like whatever would change with the exploitation. So for instance, to find I mean, we will see it, but like there is no PLM4, and I don't even use that at the end of the day because that will not work anyway. Like the ACPI table does not exist anymore. So all those things like are completely different from the exploitation point of view. But for like the compression and the SMB like functions, that's completely like based on the exploit, and it's pretty well done. Also found a bug in it because I was not able to read like physical memory like reliably, so that was improved too. Zekops and Michael Maltsev, they did some pretty good write-up on the actual vulnerability, so that was quite nice too. Some good blog posts. And I also want to give like a special thanks to Stephen Ridley because for being like so Stephen like has been doing a lot of research on ARM, published a lot of like papers and gave a lot of trainings on it. Also I've known him for a long time, so he's a good and supportive friend. And but at the time when I wanted to get an ARM64 laptop, especially last year, it was very hard to get one, and Steven is the one who basically got one for me and shipped it to me because it's like impossible to find in the Middle East. Even at some point I was like in Singapore, I tried to find it in Singapore. I think it was only available in the US at that time. Now it's a bit easier to get an ARM64 laptop. Unfortunately, and I try to find numbers, if any of you, like in the chat or watching this, like I can't find any numbers about like ARM64 laptops or machines, being used on Windows. I would be very interested to know about how many devices are in circulation now. Because impossible to find anywhere, and with the Surface Pro X now, I would assume that number is going up. Also another reason, like why doing that research was also like an interesting thing due to the timing. And so for that, obviously like to Barnaby, I was talking about it with Zero Sum. As far as we can read, is like the first person who publicly talked about APC injection techniques. So I wanted to give him like an appropriate credit. I think his paper, I mean, I'm giving him a timeline after, but like it's like 15 years ago that he released it. And also there's not many people who actually like try to use ARM64. I know like Satoshi and Peter like managed to set up a debugger on ARM64 a while back. So whenever I worked on dump it ARM64, I didn't even use a debugger, as it was like very straightforward to recreate. Also, when you like write a program, you get a crash dump. You can just open the crash dump even without having the debugger, so it makes it like very easy to debug. So yeah, kudos for them, and thanks again for helping me to set up a debugger, because there is no like Ethernet cable or anything, so you just have USB-C ports. But actually it just works like the same way, just like network debugging using like a good quality like USB-C cable from your host to your laptop, and that's pretty much it. Like it just appears as a new internet connection, and that's very straightforward. For some reason I was really expecting something more complicated, and just very straightforward to set up. A big thanks to Sean, so Zero Sum. He did a lot of work on explaining and reversing Eternal Blue and Double Pulsar. And so like a lot of his work around SMB exploitation is very helpful in general. It was here, and he's a good person I can brainstorm with for those things. Laurent Gaffier for his work on SMB. Laurent has been doing a lot of like SMB research over the past like 10 years. I remember we invited him to speak at our conference in Paris 10 years ago, where he was basically like he had so many like SMB bugs, it was just crazy. And I remember even at that point, I was like, yeah, but there's no way you still gonna find like SMB bugs like that, you know. And look at us when 2020, and there's still like so many like critical bugs in SMB actually. So on that, you know, I was picking SMB as a target. He has been quite the pioneer. So definitely like follow him on Twitter. He is posting a lot of cool stuff. Yeah, and the NSA and shadow brokers, obviously, because of Eternal Blue and double parser. I think that's also one of the main reasons people are freaking out about any type of like remote code execution in SMB because of Eternal Blue, which is pretty old now. Like the exploit itself is almost going to be like 10 years old. Like it's what, like 6 years old, 7 years old? Like, correct me if I'm wrong, but that's quite a long time if you think about it. And people are still talking about it. And there's obviously like way better exploit in the wild that we haven't found yet, which is a bit worrying if you think about it, because you know it shows you like the gap between like defense and offense, because it takes so many years for defense to catch up on techniques and find like countermeasures. It's a bit worrying. I mean, even though like anti-phishing is still an actual topic, and we're in 2020, so imagine kind of remote code execution. Yeah, Microsoft, which it's Microsoft team who found the vulnerability in the first place. Nicola Economou and Alex Ionescu for their AL research that they published. So it's quite interesting. Nikita Karatnikov, who has been a pretty big inspiration to do some work on ARM. So I've been enjoying brainstorming with him. And Suel Amu, who has been publishing a pretty interesting blog post on APCDE, so for all the event stuff, and obviously the Opcode community, and and my dog Baloo, who is here, who has been the inspiration behind the name. Anyway, I guess we can start now. Yeah, because one can patch stupid. Yeah, it's true. I mean, like anti-phishing, you're not patching anything if you think about it. People are like still pretty big on it. So yeah, one of the thing about it, so that's the version I've been using, so the 18.36.2 version of Windows, and even at some point, you know, like because I think overall, like I had to reboot my machine like more than 100 times, you know, from like the different crash, different things I was testing, you know, like just random things, you know. And once, like when I restarted my machine, it was applying Windows updates. I was like, no way, I hope I can remove them. Obviously, I can. Well, obviously, like it's not that obvious, but you know, I was able to remove like the updates. I was like, oh, it's like really. I felt like it was quite scary here. So I'm giving the name of the patch, you know. Actually, and yeah, let's just start with the demo, then I can explain how it works. Have to connect on Zoom with the other laptop to share the screen. So that's the only way I found of showing the demo. I was thinking of doing a reverse shellcode, and then I was like, oh, whatever. No, I'm just gonna do like a calc shellcode that's the same thing, and at least people won't reuse it, you know. So yeah, just connecting with the other machine. Give me 1 sec. And there should be here. Okay, cool. Continue share screen. Okay, and I think we should be able now to see my screen. So let me just move the exploit now. So that's available on GitHub anyway. Let me just like move it a bit here. So the exploit is pretty straightforward. It works the same way as it was actually. Let me just move it up. Can you see here? Yeah. Okay. Actually, maybe I can just move this guy here. Yeah. And yeah, it works pretty much the same way as the exploit from Chumpy, same parameters. And then let's see if it does work. Writing the shellcode, yes. Execution, okay. And we got our calc. That's pretty much for the demo. Now we're just gonna do a deep dive in looking at what's happening here. So as you can see, a bunch of the variables here are pretty different anyway. So there's some non-variables like the add interrupt controller, and the GIC3, which is the new name for the interruption. And then for like the whole shellcode part, I'm using a completely like a different technique. But yeah, that's pretty much it's on the other screen. It's pretty much for the exploit, and it does work quite reliably. I mean, like, look, we can punch it again and see we get another like calc, you know. So you know that's quite nice. See that it's just working like quite reliably. I guess we probably don't need the zoom thing anymore now, but that's it for the demo. At least like we can put the demo behind us. It worked, you know. Let's talk about the technical details now. yeah, like see like just like popping like quite reliably, you know. So that's quite nice, you know. Okay, let's talk about the vulnerability itself now. There is better blog posts, so the one from Huge Org and the ZecOps blog posts are like explaining, you know, like, oh, they create the MDL thing, you know, like the fake MDL and all the buffer overflow is working, etc. It's definitely explained in a much better way, so I'm not going too much over it. But for intellectual curiosity, what does an int overflow look like on Windows ARM64? So that's literally the only section about the vulnerability in this blog post. And as you can see here, so you have the add W9 plus W8. So W is for the 32-bit registers instead of like the 64-bit registers, which would be like X9, X8. And yeah, and that's it. No usage of like saved int in the kernel right before an SRVnet allocate buffer. I mean, that's pretty obvious to find. Now I'm pretty much wondering, like, why did it take that long to find? Because that's quite an obvious int overflow, and you would expect like the current static tools to find it, you know, or like whatever like you know, like methodology would be used now from like vendors to find the bug, but you know, like error happens. But because it's an obvious one, I'm sure a lot of people have found it like way before, which is like the whole thing of that bug, you know, it's such an obvious one. But yeah, it's quite nice and clean. Initially, when I was looking at ARM64, because I didn't really know like anything about ARM64 like 2-3 weeks ago, I was like, what's this kind of like weird assembly, you know? And then I got quite used to it, and I do like it now. I think it's quite neat. So yeah, kudos to Hedgehog, who is actually the from all the stuff I've read, is the guy who came up with the read physical memory page using the fake MDL structure. So that's quite nice and a pretty nice way to bypass like KSLR. So Chumpy used it by using another technique from Ulf, where she was trying to find the HL low heap. I tried to do something similar, then I tried to find like the actual PLM4, which is called TTBR on ARM64. That didn't really work out. I will explain in the next sections why. Actually, let me change the timer here. And I had to do a bunch of debugging around it, so I'm posting some of the comments here. And I have my debugger loaded in case if you have any questions or if there is anything you want me to verify on the ARM64 machine, so I can make it interactive and fun. Yeah, so here I was just like looking at the int overflow, so the allocation, and the SRV net send data function, well, to know what was the address inside my MDL. And then one thing led to another. I wanted to understand, so the problem I had when I was using the Chumpy exploit directly on my machine initially is, well, first nothing was crashing. I was like, okay, that's interesting. And then when I was, sometime it crashed much later, and then I started to look at it, and all the data I was getting was the K user shared data stuff, regardless of the physical address I would put inside. So then I started to wonder, I was like, well, it's just reading a virtual address. It's not reading the physical address at all, like I was promised. I was wondering if the behavior was different on ARM64. Then I saw also some issues on a GitHub repository where people were complaining, saying, oh, the read primitive was failing. And then I started to look at the MDL flags being used. And I ended up using the 5018 flag instead of the 51C, which is removing the MDL source is non-page pool. And the reason I ended up removing that one is while I was looking at the code, and I started to like remember about the get system address for MDLSEF macro. So even if you see it in the code, you will not see it because it's a macro. But there is always those checks on the MDL flags, checking if so if page pool, so if the flags are mapped to system VA or source is non-page pool, then it would use the map system VA. And if not, then it's using map log pages specified cache, which is what we want to be triggered, because that's where it's gonna like start to read the actual PFN of the MDL. So when I started to see that, I was like, oh wow, actually that's interesting. And then I was like checking the flags. I was like, well, the MDL source non-page pool flag is present. What about I just remove it? And I remove it, and it worked. I could read like physical memory. I was like, oh wow, that's good. Except, okay, like it comes with some like terms and condition. You can read physical addresses, but if the physical page is not visible, if it's not actually mapped, if you're like asking for a random like physical address, it's either gonna hang or you're gonna get a blue screen. And also the other reason is if you cannot lock a page, which is what I suspect is happening with like the page tables. And we're gonna see like in the next session why it's a bit annoying. But you're gonna end up in a similar situation with hanging or crashing. So, and actually it reminded me, like when I initially wrote dump it, like everyone was like, oh, like doing a digital forensic, like we want like raw memory, this is what it should look like, we want just like a raw dump, we want a vmem type file, so everyone was reading from 0 to the highest physical memory address, and that's was the idea of like raw dump, partly from like law enforcement, being like, oh, we use NKs, we use raw dumps, we load it in NKs. So it was the mentality, and it's still around, but it was having a lot of issues, and rightfully so, because you have physical address space and RAM, which is two different things, and physical address space as the RAM plus the memory used by graphical devices and all those things. So if you try to query the memory of another device, you would get a crash, or it would hang. And then, in my presentation, like blue screen of death is dead, I was explaining like the basic things about like what's physical memory layout. And there is a very interesting function in Windows called mmget physical memory ranges. Actually, it's funny enough, because my old blog, I didn't renew the domain like a few years ago, and but I managed to retrieve that blog post on the Chinese website. But yeah, that function is giving you like memory ranges, and we'll use it like later on in the blog post, you will see. And like the memory, physical memory runs and descriptor are the actual structures that give you like the memory ranges used by the RAM, and at which physical address they are inside the physical address space. So that's something to definitely keep in mind. And also, the second reason, because I was wondering, I was like, oh, okay, like how come I cannot read like none of the page tables? Because initially I was like, okay, like Jumpy is getting like the PT, thanks to our Chinese friends for making backups of my blog. That blog post is like, I don't know, like 12 years old, So that's pretty cool. Yeah. And then I was like, okay, I'm like, Champy is using this technique, which is like reading a page table, trying to find a self-reference to the PML4. Okay, and then like you can get the virtual address to override the care shared user PT, which is something I was doing manually in the debugger for like the longest time, until I was like, I'm kind of annoyed to just like tap the command to know like, okay, what's the virtual address of my PT, and because I was not able to read it from the exploit, right? And there is something I read in the documentation, so I put the link here, so if you want to read more about it. On ARM64, and I don't know if this is the case with all the ARM system, you can have multiple physical address space. So you have the secure or the non-secure physical address space. They may or may not be the same. So that's something to keep in mind. And I was like, oh, actually, that's quite cool. So both worlds do not always have the same physical address space. So at this point, I don't know if when I was in EL1, which is like kernel mode, I was in secure, non-secure mode. And if it was the reason I could not read the physical address space, because when you're using Windows Debugger, you can actually read those page tables. So I was like, I don't get it. This is definitely at this address, like what's going on? And yeah, so so that's the two hypotheses. Either it's not mapped or it's locked, so you cannot just like relock it, and just like a separate physical address space. So there's a few things here. So whenever you want to retrieve the TTBR one address. You can use the PCR structure, which is quite nice actually. Let me just show you here, or you can. Oh, I'm typing on the wrong screen. So you can retrieve like the actual structures and address for like your main page tables very quickly. So let's look at the PRCB and then process state, and then we have this one called arch state inside the processor state, and that's where we get the address of our TTBR. It's like, so that's the main one. So we have the so EL1 kernel, and then with the secure and non-secure ones. So that's how we can look at it. And then, you know, if we actually look at it, you know, we can actually read it inside Windows Debugger. But if we look for that same physical address, and yes, there is an 8 at the beginning. We'll see why after. Yeah, there is that's not readable from the exploit, although that address does exist. And another like variable which is interesting, which we'll use in our shellcode, is vbar EL1, and vbar EL1 is the ARM64 exception vector. Bruce Deng actually wrote a pretty nice blog post about like how it worked. I found it after actually when I was like trying to search more information about vbar EL1. But yeah, so if you're coming from x64, TTBR0 is basically like the equivalent of like the PML4 or CR3 register. That's like the main thing you need to remember. And the interesting thing here, first, a very interesting thing we're gonna find out is on my machine, the page table, so for like the TTBR PFN, has consistently been that address. I've been rebooting it like more than 100 times. Like 50 is a very conservative number given the time I spent on this. And even if you look here, I just tried again, it's the same value. So I'm not saying it's static across all the machines. I'm just saying it's static per machine. So if you know it once on a machine, like very likely it's always going to be like that, unless like some changes have been made like recently, which I'm not aware of. Yeah, that address is quite consistent. And here, let me check, does it work? Yeah. And from debugging the actual bootloader, so if you look the call right after, so boot mg fw module, so there's a function called ARM64 pallocate and initialize page table, which allocates like the main, you know, like TTBR that returns this address. So to understand how the address is being computed per machine, or to do some prediction, like I or we would need to look at that specific function and what's the logic behind it. But I didn't have time to do it yet. But that's basically where the answer would be if we would want to know the exact answer of why it's static. So initially when I saw that, I was like, well, that's quite nice. We have like a TTBR, which is static. So I should be able to read it and find the self reference to the TTBR, so I can get the, you know, like the virtual address, and then find the virtual address of the PT I'm interested in to like flip the NX bits, right? But like I was saying, like it didn't work, you know. So at this point we have two main assumptions. KSCLR is only used on kernel virtual addresses, but it does not seem to be the case for early physical addresses. So we have KSLR for virtual addresses, but not for all the physical addresses. The second point is, but unfortunately, we cannot read physical page tables. Well, let's think a bit out of the box here. What's the other PT that's created very early that we would be interested in? What about AHLP interrupt controller? But guess what? It worked. I was like, oh my god, that's crazy. So here the PFN is always like 80009 on my machine, and that has been like very consistent across a few machines that I managed to look at. Unfortunately, they were the other ones were patched, so I could not like have tried the exploit. But so the terms and condition here is, so the exact answer is, okay, the static address is not always like 8009 as a PFN, but the logic is the same. Is so where does it start with an 8 in the first place, right? Like where is it like 8000 or like 80,000? So the reason it is 80,000 is because if you look at the actual like physical memory descriptor I was talking about early, like here when I was talking about that function here in my blog post backed by our Chinese friends, the actual physical memory descriptor here in my case start with 80,000. And on my friend's machine, who had a completely different laptop from a different brand, it starts with 40,000. And then, so you just take the base page of the first physical memory descriptor, and even here, you know, like let's look at it. So see, it's like it is like 80,000, and then you can see like the other ones, like it's mapped completely differently. So it is the base page plus 9, and then you get your PFN. So in theory, and I tried in my case, I was like, okay, what happens if I try to read that physical address on my machine, and then the one that I know is valid. So when I tried to read this, I got a blue screen, you know, it was hanging, because initially I was like, well, in that case, if I just need to try like 2 physical address to get the interrupt controller like PFN, like that's definitely worth it. But you know, if you get it wrong, like it's gonna crash. So it would have to be like brand specific or like something like that. But I'm sure there's like better ways to find it. But that's basically like the logic behind it is whatever base page you have plus 9, and then you have the PFN of the you know, or like HL interrupt controller. And then if we look here, because we like nice things, it does look familiar, except that instead of the epic functions, we have the GIC interrupt functions. And yeah, actually, like I can show you here the logic of what's going on here. But if we look in this function, so read interrupt controllers, that's basically where I'm reading sort of like my physical address, which is a fixed address. I read it. I do some like very simple heuristic at this specific address, which is here. So here I know it's a size to verify the actual like structure that it is the right structure. And there's few informations I want to retrieve here. So first of all is the actual virtual address of HL interrupt controller, because we're gonna need it when we're gonna patch one entry in it. The original address of the GIC3 request interrupt, because that's the entry we're gonna patch. And yeah, and its virtual address. And and that. Yeah, and that's the second, the last information we do care about is the HL virtual address. So here I just make a subtraction because I'm just taking the virtual relative virtual address of interrupt controller, because we'll see why in the next section. So that's the heuristic I was talking about. So here, static verify the address. We do care about the base address of HL for later stage. So that's the offset, the delta I'm removing here. And so what I was saying is APIC does not exist on ARM64. So one of the things which is different is APIC is replaced by something called generic interrupt controller, and there's multiple versions. The version implemented here is 3. I think the latest one is 4. And so yeah, it defines how to handle like all the interrupt, obviously, and it can be like uniprocessor or multiprocessor. In our case, like we're gonna patch the request interrupt entry just to be faithful to the APIC version where we patch the APIC request interrupt. If you call IO remap to create a new mapping for RAM, won't the multiple mapping have different attributes? I don't know, but if you do know the Windows equivalent of that function, I may be able to answer. Like I'm really bad at Unix stuff. For the push pop instruction though, we're gonna see this like quite soon. Like it's the section right after, because I'm gonna be talking about the shellcode part. But first, like we're gonna see like we're gonna bypass like KSLR here and the non-execution also. So there's two methods here that we're gonna see first. So yeah, so K-shared user data is a popular option to copy and execute payloads because K-shared user data is a fixed virtual address. And so that's what I was saying, that's what I tried initially. I was like, okay, let me look at it, like I can retrieve the PT. So just hard coding the PT, just from like typing the virtual address and taking the value in it. One notable thing though, in case if anyone like can find a technique for that later on. So what we do care about are those two entries, because the PT format is similar for reading like page frame numbers, but not for the other flags. Actually, they are very different. So there's two PT that we care about is privilege no execute, which means no code execution in kernel mode, and user no execute, which means no execution in user mode, which is EL0. So if you flip those bits, which is basically what I do here, you put both of them to false, and that's it. In theory, like your PT will be executable. But like I was saying, remember, we cannot read physical page tables with our MDL assisted physical page read. So I was doing that technique like with the help of the debugger, like I was like finding the PT and everything. So it was pointless because we cannot use it in practice. Then I started to wonder, I was like, why would I even like try to do like everyone and just use like shared user data when I'm sure there's a better way of doing it. So why trying to find a PT and flip it just to execute code? I'm sure there is like other like pages we can use to put our code, And then I started to look at the base image of kernel modules. And one of the things I noticed is, they're all executable. And why? Well, I'm even making jokes in that blog post. It's getting serious here. So I love big pages. I cannot lie. Why? So because the binaries are mapped over like big pages, and like the header page is not on a 4K page, and then binary on a big page which is executable. The whole binary is executable. So if you take the code of the binary or the header, it's going to be in an executable PT, which is quite nice. So what I ended up doing is, remember like here, I was saying, okay, we do have the virtual address of registered interrupt controller. So we can retrieve the actual base address of the HL module. So you see here, we get the base address, and yeah, we have the base address of the HL module. So that's quite nice, because now we do know where we can copy. Yeah, and here, I do check like the PTE, and as you can see, not executable. Well, no, it is executable because the non-execute flag is off. So if we just put our shellcode at like HL plus 500, because I didn't want to overwrite the original header. Because also imagine you overwrite the thing to write your shellcode, and then with your shellcode you try to read the export table, which was overwritten by your shellcode. It's like so that would be quite stupid, right? That's one of the main reasons also we don't do it. So yeah, so we do know where we can copy our shellcode. We don't need to do any like PT, like non-execute bit flip, and we do know what we can patch to get the initial like jumper for the code execution. So now we're getting the shell coding. So and this, I didn't have time to try it on 64-bit Windows. I would be definitely interested. But it's quite a neat way of like bypassing KSLR and execution. Well, non-execution, I guess. So the first thing about our shellcode is, so there is no Persian pop, like someone just said in the chat. So Destructive Research Labs. That's quite a long nickname to read. Like I have to focus. Indeed, but there are registers, and a lot of them. And also one of the registers which is quite interesting here is the link register and the frame pointer one, but the link register, so every time you do a call anyway, that value is going to be registered. So whenever we're going to want to exit the function, we want to make sure that especially that register is set to normal, to the original value. Otherwise, whenever it's going to hit a write instruction, it's not going to return to the write instruction, and you can end up to some sort of like infinite loop, but it would crash like way before anyway. So to re-implement a push add and a pop add on the ARM64, so that's how I did it. So I created like a fake frame on the stack. So, like very straightforward way, like just allocate the space on the stack and store all the registers from X0 to LR to the stack. And when you want to read them at the end of your shellcode, just restore them. That's your pop add. So instead of having like a 1 byte instruction, you end up with 4 bytes, per instructions. But you know what? Because of this, we have like B100 like byte of space anyway for shellcode. So why not? Why not? What else? What else do you need? Even at the end, like that shellcode could be like even like much bigger, because it's a lot of space, basically. I can probably put like some demo making video in it instead of like a calc, you know. That would be a new type of demo. So we have a push add, pop add. The next step is, okay, how do we get the address of the current process? So also there's something interesting happening with the x18 register. So it has two names. So in Windows Debugger, they would use that notation, which is, I mean, I prefer that one because it's the least confusing, because all those like registers sound the same. Or the IDA notation, which I'm not a big fan of because it's very confusing, and same thing for like the you know, like the MRS and MSR instructions. It's much easier to read on Windows Debugger than on IDA, because this on Windows Debugger, as you can see, okay, like you can see what's going on here, but in IDA you would see like C0 or C2, like unreadable. So it's quite confusing. But anyway, so XPR in kernel mode is pointing to the KPCR structure, so we can just like read it, get our thread and process, and in user mode it's gonna point to the TEB, which is also something we're gonna use for our user mode shellcode. And once we have like our current e-process, then we can obviously like walk through all the process to retrieve the kernel base address. So we're gonna use that register I was mentioning before, so the vbar EL1, so the Victor base address register for, and as you can see, it does say, you know, like EL1, so that's the version for the kernel, where we get the KI ARM64 exception vector function. So for all the exceptions, it's going to go through that function. Bruce Deng wrote a quite nice blog post actually about it. So yeah, he was explaining like, although it's not really relevant for the shellcode, he's kind of explaining. See, that's the notation I was talking about from like IDA, or this, you know, like it's I mean, I don't know, like like look, even see, like just to like it in Windows DBG it would be like MRS X1 ELR underscore EL1, you know, like, okay, like you kind of know what's happening, but like look at this, like 0, like C4 0, like 1, you know, like I mean, definitely needs some macro in IDA to understand this, because like let's say we look at it now in WinDBG. See, get the first one. It's like MRS XPR TPIDR underscore EL, you know? Okay, like that we can understand. Then you have like the IDA version, which is like X18, you know, instead of XPR, and all those things behind, you know, like very, very, very confusing. Definitely not very user friendly to read. Same thing, see, like same thing for like ELR, the like all those registers here. You know, like it's very hard to read the IDA notation for that. Very hard. Which is funny, because if you use the Windows Debugger notation anyway and compile it with your compiler, like your assembly compiler, it will work anyway. So I mean, I'm sure we're gonna see an option in the future, but I do hope so, because it's unreadable. Anyway, so to get the NTOS kernel base here, so we just get the exception vector function address, and you know, we clear the bytes, which is what we do here. And yeah, we just like subtract the base from it, and that's it, and we work backward. And we check the signature. If it's an MZ, that's it, we have the base address. Another interesting thing also for the shellcode, which is ARM64 specific, is they have a bunch of RCE32 opcodes. So that's quite nice, especially when you want to hash functions, because instead of doing your own hashing function or whatever. So in my case, I was just using my own hashing function, which was using the CRC32B like instruction. And yeah, so I have this clean way of like hashing like function name, and that's pretty much it. Another cool thing also is, and I got the idea from brainstorming with Zero Sum, is so if you look now, all the Windows like kernel shellcodes, they all use like APC twice, and even like SMBaloo actually like wrote this nice blog post actually last year about it. Was it last year? Yeah, last year. Saying like ATP is using ETW to detect user mode APC injection from kernel mode. It's a good blog post. I would recommend you to read it. It's quite straightforward. But yeah, so there is an ETW event to trigger like this, and actually also like Huge Hog mentioned in his blog post that he had to patch one of the function from from kernel mode, but in user mode, which was the NTDLL equivalent, which is here. My kernel on shellcode is a very orthodox one, APC twice, didn't work at first. While writing the kernel shellcode, I found that the user CFG recognized the APC call for user-alone shellcode as invalid and intercepted it. As you can see from the screenshot below, KI user APC dispatch calls LDRP validate user call target before jumping into the user shellcode. So there's potentially like two annoying things that we don't want to have to do, and we don't want to have to look for like the NTDLL function and patch this function, like he had to do, like we can patch the function. It's actually quite nice that he shared that, because that's the first time I heard about it. So that's also something I wanted to be aware of. And I was like, yeah, you know what? I'm just gonna like try to see if there's a better way to do it. And if you look even at the APC like injection in user mode, it had been like people have been using the same thing for a very long time, since 2005. Like when Barnaby Jack initially published it. I did write about like kind of like the blind spot of some EDR, because a lot of the EDRs now anyway are like relying on the ETW events. So I was talking about the history of the APC techniques, how it kind of became more popular for injection, and or like we are detecting it, or we're like doing some different type of detection for like such things with our platform Stardust. But yeah, like everyone has been using it for a long time, kind of like annoying. But the good thing is with Windows 10, there's this API that appeared, which makes our life easier. Exported by the kernel this time. It was always exported by NTDLL, but now it's exported by the kernel. It's called RTL create user thread. So now guess what does it do? Yes, it's beautiful, and it does work nicely. I mean, I've been laughing during the whole time I was writing this exploit, because I don't know anything about exploit. I just wanted to learn ARM, I mean, I read stuff about exploit, but I don't write exploits. Zero Sum also wrote a nice blog post about ring zero escapes. He didn't cover that one, but I did try it, and I didn't try it on x64. I tried it on ARM64. It worked fine, you know. I'm pretty sure it works on x64 also, because it's also exported. And the way it works, so that's the actual like pseudocode of my my shell code. So you don't have to read like all those crazy like registers. So I use one APC once to get out of that super high like IRQL, you know, and just like resume back the execution, you know, to the normal state, you know, because I don't want to stay in that RQL mode, and I don't want to change the IRQL in that specific mode to avoid any problem. And then to lower my IRQL, so here I could have hard-coded the actual like RQL change, you know, for like to go from to passive, you know. They just overwrite it in the PCR. But since I had the base address of HAL, you know, I was like, you know what, I'm just gonna play safe. I want to do something clean, so I'm just gonna call like kflower RQL and kfrise RQL just to like have something nice. Then I use like k stack attach process to be in the current e process of my target process. I just decided to allocate, you know, like just a nice like 1000 you know, like one page in my user mode virtual address space. For the handle, I just use -1 because we did the stack attach process. We don't need, I mean, I've seen people like doing that where just like, you know, like do like the NT process handle and pass the handle. Like, doesn't make any sense. Yeah, then I just do like a homemade mem copy, and then I call my RTL create user process. What else do you need? It's like, what else do you need? So on x64, you know, like shellcode, you see like STI, CLI to enable and disable interrupts. You can do that the same way here. I mean, I just used it only when debugging, but not in the version you saw. You know, it's not a version that I want to debug anyway, so just removed it. Because it was not necessary. And after we call our popad, we just pass the execution back to where we want to go. And so yeah, the equivalent of a jump, you know, like registry is BR x8, and the red never gets executed anyway. And because when we did our pub add, we restored the LR register, which is the return address, then we were good to go, you know. Actually, let me show you the actual. I mean, you can see it on the. If you go on the GitHub, anyways, is the full full shell code, you know, which is here. Yeah, here are some notes, you know, that I had before. So like that's the push add. That's the internal base address, you know, where I keep saving all the you know, functions and values that I like and want to use. So like the base address, the process object, same thing for like the other objects, the single APC we are using. That's the hash for all the functions and process. Yeah, and that's pretty much it. Like if we cannot allocate the memory, like it fails nicely. No, yeah, and that's yeah. Overall, that's pretty much it. That's the get process address, which is exactly the same one in user mode. So if we look at the calc shellcode, so same thing. it's gonna use for the hashing like the CRC loop that was mentioning with the CRC32 byte instruction. Yeah, calling our function here. I didn't put a full like per chat per pad, you know, because you know whatever, it's like in user mode, and that was fine. But yeah, that's pretty much like the same way. It's more compact than the actual because initially I was like allocating a small stack and everything, but at the end I'm not even like doing all of this. I'm using a much more compact version. And yeah, that's pretty much it for like the user learn part. So remember, like x18, which is XPR, is pointing to TEB in user learn and the PCR in kernel mode. So once it's being executed, so we are in EL0. From the TEB, we can access to the PEB, and then from here we can just like work the DLL just like a regular shellcode. And yeah, that's pretty much it. So pretty stable overall. Like the KSLR bypass, because there's no like physical address, SLR is working nicely. No need to patch a PT. Yeah, overall it's pretty nice. Conclusion here. Memory forensic is dead. Long live to memory analysis. I stopped calling memory forensic. I just like call it memory analysis, because at the end of the day, all the things you have to do now anyway, like if you want to find like like stuff in memory, like let's say, you know, that's HL. I mean, in theory, like we should find our shellcode here, right? And here is our shellcode that was executed, is still in memory, right? So you can see like the post exploitation detection for it, because obviously, like I was saying, you know, like the goal of that blog post is to be educational, because it's interesting to understand techniques, but at the same time also to understand how to better detect. So here in that case, because the interrupt controller entry is going to be repatched right after, right? So unless you do clean your shellcode right after, it's still going to be present in memory. And here, as you can see, that's our stack frame. And all those beautiful operations we have been talking about, you know, even here we can see like we're trying to retrieve the either the NTOS kernel address base or the HAL address base, but I think it's probably the NTOS kernel address base, because yeah, we do have HAL already. And yeah, I mean, and all our get process calls here with all the hash and everything. Yeah, I mean, it's quite nice. Like, so that's why I just call everything related to memory and detection and defense like memory analysis, because it has nothing to do with what people like call memory forensic. It's so far behind. I mean, I was saying it at the beginning of the article, people are still stuck with like the raw dumps and all those things. It does not work for like modern attacks. For instance, here, how do you want to detect attack on ARM64? Nowadays, you know, like as far as I notice, is like the first public exploit for Windows ARM64. You know, there's like Surface laptops being popular now. You can't. A lot of like those tools don't even work properly with Windows 10, you know. So let alone like ARM64, although it's not as popular, it's gonna be the excuse that people are gonna say. But you know, like I don't think it's an excuse for defenders to be like behind attackers all the time. So that's why I still think it's interesting to like look at all those aspects. So in that case, one of the things I've been pushing for is like, at least if you can get like a post-exploitation memory dump here, while you can still like retrieve the shellcode like we just saw, like, and there is like different places where the shellcode can be like in place, like in the case of the Chumpy exploit, you would see it like in cache-shared user data plus 900, because that's where, like the fake MDL and like shellcode and everything are being copied. So, but yeah, that can be in different places in memory. So that's why having like an actual like, like Microsoft crash dump, which is like what things like dump it, I mean, are generating. Or if you get like a blue screen of death, then you can get a memory dump. On Linux, we've been doing a bunch of research on Linux. Yeah, same thing, like we're using a like elf core dump for like full memory. And on Linux, I think it's even more interesting because a lot of like the actual like even like the EDR detection, a lot of research is done for like Windows stuff. On Linux, there's like almost like nothing. There's few like Linux presentation that we accepted for Black Hat US this year, so that's interesting. But if you look at all the cloud servers, most of the things are Linux. And the only thing people are talking about is like anti-phishing products because of like BC stuff, or like how to use like OS query for incident response, and when 2020. So I mean, it's a bit depressing, but I mean, I stopped trying to like even like get emotional about it, because whatever, if people think like OS query is gonna protect them on their Linux machines, when they cannot even like investigate like post exploitation like techniques or anything, yeah. So if you do like Linux exploitation, same thing. Like I'm sure like people will not find anything at all. Whereas like here, even on ARM64, like you kind of like make a short list of places to look at, make some playbooks. At least that's something we're attempting to do like internally. So it could be like detection playbooks and detect them. Well, you can find stuff after a while when things are not supposed to be there, right? But yeah, that's pretty much it. And I think it should be, I mean, like obviously, like I was saying, is like for ARM64, like no one does any detection for it. Like EDRs only announcing like endpoints now for Linux. They're quite proud of it. But if you look into details, even if you ask like a lot of their customers, they're like they know it's shit, But what do you want to say? But yeah, it's kind of sad that defense is just like kind of limited to like converting like IT tools into like DFIR like utilities, but cannot really convince people that whatever they have learned is a bit useless and not how they should be doing things. But yeah, so that's pretty much it. Although I hope I was not too much of a downer at the end, didn't mean to be depressing. But yeah, everything is on GitHub. Even the full blog post actually is on GitHub. Looks quite nice actually on GitHub. In case like if my website shuts down and some Chinese friends want to do like a backup of some of my articles again, at least it's on GitHub now to be easier for people to do a git clone. Yeah, the full exploit is here, the kernel shellcode, the user non-shellcode. Yeah, if you look at the exploit file, you would see like most of the stuff that are being described here. And yeah, and that's pretty much it for my presentation. So if you have any questions, you're more than welcome to shoot them. Otherwise, if you have no questions, you're more than welcome to join us on the Discord server. So we're always there. How long of a period of time did it take this for you to? I would say around 2 weeks, 2 to 3 weeks. Because I started a bit before the other like opcode. I was kind of like, I was hoping to finish and everything. Yeah, and I finished like 1 week later. So I would say like between 2 and 3 weeks. From like learning how to set up like the debugger, learning ARM and all those things. But yeah, it's quite interesting. Like I was saying, like ARM actually I didn't really like it at the beginning. I found it very confusing because I was so used to like the Intel syntax. But it's quite nice actually. I do like it, and yeah, I'm also trying to learn a bit more about like embedded device because all of them are ARM. It's not ARM64, but you know, like I do feel like IoT is definitely gonna have an interesting like space. A millimeter this morning actually, but yeah, I think there's lots of cool stuff to do research-wise, you know. But yeah, so you guys are more than welcome to join the Discord. If you have any questions, you can shoot a message on Twitter. Or just like come join on Discord. You know, we start to have a pretty good group of people. Like it's kind of like a close group. Like we're not that many. We're just like few hundreds. But most of the people are like really good researchers or like, you know, like teenagers who want to learn more about security or like IT and all those things. So it's a good mix of people. Everyone is behaving like nicely and everything. It's just like I'm just trying to recreate like the atmosphere of like IRC like 15, 20 years ago, you know, when it was nice, you'd ask questions, you know, like although before like we didn't have like Stack Overflow and all those things, but I do miss like IRC a lot. I do feel like it's quite an instrumental place, you know, when you want to ask some things or like look for a job or all those things. So yeah. Subscribe on the YouTube channel and come join us on Discord. And yeah, if you have more questions, yeah, don't hesitate. I'll put some background music. Actually, I don't even know if the music is working. So that's it. And no more question. I guess this means that this is the end of this live stream. So also, if you do want to present for the next opcode, the call for paper link is available on the website. You're more than welcome to submit. So this is edition 8, we have 9 and 10, and I think after 10 maybe like it's time to take like a bit of a break for a bit when there's like more like cool presentations. But yeah, and yeah, just like at least you know that all the links are available on the GitHub for the other presentations also. I'm gonna put the resource also on the GitHub, and thanks to our speakers today, so Grok, Corentin and Paul. But yeah, that's pretty much it. No more questions, no more comments. I guess it's time to let you go, so I can get some food. Getting thirsty here. It's like 40 degrees in Dubai. Okay, guys, take care.